All right. Next Coulomb's law problem. A lot going on here. Two small objects, each with a charge of -4 microcoulombs. So some language we have to pay attention to. Microcoulombs. -4 microcoulombs. That means -4 times 10 to the -6th coulombs are held together by a 200th meter length of insulating string shown right there. The objects are initially at rest on a horizontal, non-conducting, frictionless surface. The mass of the first thing is about twice the mass of the second thing, and the effect of gravity on each object due to the other object is negligible. So, all right, draw a free body diagram of the forces. So here, let's see, they're resting on a table. Right? They do say that. They're resting on a horizontal frictionless surface. So we've got a horizontal frictionless surface. We've got M1 here, and we've got M2 over here. Now, let's go to forces. Let's go forces. This has a charge of -4 microcoulombs. This has a charge of -4 microcoulombs. Like charges repel. So there is going to be an electrostatic force repelling these two. And you have to be careful. I didn't do such a great job, but I did pretty close. You should touch the object there. It's got to be touching the object. And the length of each electrostatic force arrow, the objects are at rest, so the forces are going to balance. They're the same charge. Object 1 is pushing object 2 away. Object 2 is pushing object 1 away. Equal and opposite charges. Equal and opposite forces. All right, what else we know? Well, there's a string holding them together. So there's going to be a tension in the string. Right? There's the string holding them together. Same string, same tension. Again, it's at rest. These should all be the same length, same size. I'm doing a pretty bad job at doing that, but okay. Then they're sitting on a table. So the earth is going to be pulling them down. They tell you that the M1 has a mass that's considerably larger than the mass of the second object. So the table is going to be pushing up as well. Force normal. Force normal. All right, draw a free body diagram, label the forces, not components. All right, I think we got it all. Those are all the forces. Right, gravity's pulling it down, normal force up, tension that way. There is another force, the force that we were told to ignore, right? The effect of gravity on each other. Every object pulls on a gravitational force of every other object. So there is a really, really small gravitational attraction between them, but we're told to ignore that. So we can just get rid of those arrows there. Those are negligible. Okay, so there's your free body diagram. Now let's look at the tension in the string. If we were to look at the tension in the string, we could examine any one of these up close and say, well, tension is horizontal. So let's do sum of the forces in the x direction equals MA in the x direction. It's at rest. It's not accelerating. So the force to the right minus the force to the left equals 0, or the electrostatic force is going to be equal to the tension force. we have to calculate one of them. The one we can calculate is the electrostatic force. The electrostatic force. This is very, very, very similar to gravitational. Electrostatic force is K Q1 Q2 over R squared. Very, very similar to gravitational forces between two planets or something like that. Right? Remember, F sub G equals G M1 M2 over R squared. Very, very similar is the electrostatic force, but different. The electrostatic force is equal to K. K, the electrostatic constant, is 9 times 10 to the 9th newtons meters squared per Coulomb squared, multiplied by Q1. Q1 is negative 4 microcoulombs times 10 to the minus 6th coulombs. Q2 is minus 4 times 10 to the minus 6th coulombs. In fact, if you want to get rid of the negatives, you can ignore the negatives because in the reference tables, we just really care about the absolute value of this, sort of. And then you divide all that by the separation between them, which is 0.020 meters squared. So let's see, grab our calculators, do some math. Remember how to use scientific notation in your calculator. 9 second EE9 times 4 second EE minus 6 times 4 second EE minus 6 gives us 0.144 newtons meters squared over 0.020 meters squared. Divide those things by each other. 0.14, divide that by 0.020 squared. That gives us 360, I believe. Double check my math. Divided by 0.020 squared. Yeah, 360 is right. 360 newtons. And if the electrostatic force is 360 newtons, then the tension in the rope is 360 newtons.